All right, so let's just do this. We're going to take a look at 10.2 and a little bit of 10.3 together. A bit of a combined lesson. 10.2 is short, 10.3 is long. So we'll see how far we get here today, okay? But we've talked about sums and differences, right, of functions. And today we're going to talk about products and quotients of functions. And I mentioned yesterday that we just got through Chapter 9 studying rational functions. And really, rational functions are polynomial function divided by polynomial function, right? That is a quotient of functions. That's basically what we're talking about. So if we go to our notes here, products and quotients of functions, we can multiply two functions together. And we've done that a ton of times. And I'll just make a little bit of space here so I can show you. We've done that a ton of times. For example, we've done x plus 2, for example, times x minus 5. Hey, this is f of x right here. F of x equals x plus 2. G of x equals x minus 5. You multiply those together, what do you get? You get x squared minus 3x minus 10, right? Well, that is f times g of x, or f of x times g of x. So we can do product, okay? We can also do quotient, which, like I said, we studied extensively in Chapter 9. This is the notation, so just like we have special notation for the sum and difference of functions and for this multiplying of functions. Notice this is a solid multiplication dot, okay? And yeah, so we can also divide functions. So for example, we can divide f of x and g of x here, and that would give us x plus 2 divided by x minus 5, right? And so that would be f over g of x. We won't use this notation a lot, but you'll see it in the textbook, and I'll use it once in a while. So again, just a rational function, but we understand that it's comprised of two polynomial functions. Okay? Now, the actual meat and potatoes of this is just that. Now, we can simplify things, right? We can notice asymptotes or gap discontinuities, all that sort of stuff. What we're going to be focusing on a little bit here in 10.2 and 3 are word problems, okay? So where we have ratios of different things, okay? Now I have a video already up on a lesson on 10.2 where I go through example 3 in your textbook extensively. So we won't take the time today to go through example 3, but I would encourage you, where is example 3? Oh, there's 2. So example 3 in your textbook is this one right here, an application of products of quotients and quotients of functions. So that is a very good example for you to go through. I'm not going to go through it today in this shortened combined lesson, but you should look this one up. Okay? So yeah, products, ratios, different things. Okay? So that's example 3 on 10.2. What I would like to continue on with, though, is talking about the domain and the range for quotient and product of functions. And we talked a little bit about this last day as well. Okay? The domain of a product or a quotient of functions is the domain that is common to both functions. Do you guys remember us talking about that yesterday? So if we combine functions at all, the domain, that is all the allowable values of x, the domain for that combined function has to come from the valid domain of each of the functions that make it up. So in this example, what we're going to do is we're going to simplify and we're going to state the domain. Okay? So this looks like a rational function. Obviously, this is a ratio of two different functions. So I'm going to have f of x, let's make that the top function. So this is f of x, which is x squared plus x minus 6. And then we have the bottom function, g of x here, which is 2x plus 6. So if we were to look individually, let's talk about the domain right away before we do any factoring, simplifying, anything like that. Let's take a look at the domain. All right, well, we might have to factor these to actually kind of see the domain. But f of x, remember, is in the numerator. Okay? So within f of x, I don't see any square roots that would make me think, well, it can't be negative under the square root, right? We can't do that. But there's no square roots. No problem. We're not dividing by x at all in this function. So there's no, divide by 0 flags. And this is in the numerator, so we can have any real number in the numerator of a function, right? Any number at all. Positive, negative, rational, irrational, decimal, whatever. So the domain here is all real numbers. Okay? X is an element of all real numbers. And that's all you need to put there for domain. Now, the domain of this function as well, okay, is all real numbers as well. But what do we know about this function as a whole? Okay? So the domain right now is we're okay with every single value, right? Every single value is okay if we look at the functions individually, and that's always where you start. Okay? The combined function now, it's actually easy to see that I have a restriction now that I combine the functions, because we can't divide by what? Okay? 0. So if we look at this little note here, this is XER, this is XER. So you might think that the combined function should have XER as well. Well, if you're adding, subtracting, multiplying, that's okay. But the dividing adds the added little flag here of the denominator, right? So this is good, but the domain is not XER, and it's pretty obvious. We do have to do one more check. The domain of this is what? Of this entire function is? It's XER, but X cannot equal what? Negative 3. Very good. And you can just state it like that. Okay, X cannot equal negative 3. So any other real number but negative 3. Okay, so then we'll simplify, and it doesn't matter which order, I guess you do it now, but we'll simplify this now. So can we factor this numerator? It's a trinomial. Looks like if we can find two integers that multiply to negative 6 and add up to positive 1. Sorry?
X minus 2 and X plus 3.
Good. X minus 2 and X plus 3. Those add up to positive 1 and multiply it to negative 6. Very good. And on the bottom here, you know what? We can factor this as well. I can take out a common factor, and I got X plus 3 on the bottom. Okay. And so you know what? Here's where we can easily see this whole X can't equal negative 3 thing, right? Because we have this. So if you don't see that when it's factored, go ahead and factor, and then you can identify, right? All right, so are we done? Or can I simplify this rational further? Yeah, you guys are on the ball here. Absolutely. So we have a common factor. Okay, a common factor. Now, can I do this as well? Can I divide out these 2's? I can't. You're absolutely right. Why can I not divide out those 2's? Because that happens actually in high school. Kids try and do that. Why can't we do that? The 2 on top is a part of the this binomial. It's not standing on its own like the 2 on the bottom is on its own as a factor. So you can't take a piece of a number and divide it out with another whole number. It's kind of like saying 12 divided by 2 is 1, because I'm going to just cancel out the 2's. Yeah, and it's actually not, okay? Okay, all right. Okay, so, very good. So now what we have is we have y equals x minus 2 over 2, or you can write that as 1/2 x minus 2, okay, whatever you want. And, or, I mean, you could go 1/2 x minus 1, okay, with the caveat, or with the one little qualifier that x cannot equal negative 3. It's undefined there because of our original function. Is that good so far? Now let's see. This is a straight line, isn't it? So I've got this up on Desmos here already, and so you can kind of see it right here. Y equals. I'll just throw the y equals so that you can actually see it on the video. Should you watch that? Because the video cuts off about here, I think. So if we look over here, this is a quotient of two polynomial functions, and it looks like we have a straight line here. We have an intercept here, we have a y-intercept there, that's great, but at negative 3 down here, so watch what happens at negative 3. Oh, do you see that? Undefined. That's our restricted value from the original quotient of function. Okay? So you guys remember this from chapter 9, right? Studying rationals? Okay. All right. Okay, good. So that's a little bit on that. Now let's take a look at. Are you guys okay with that? Any questions? You guys look like you're nodding and having a lot of fun. Are we having fun? I'm the only one that's having fun? On this fine Wednesday? Hump day? Come on. All right. Okay, let's take a look at this type of question. This type of question right here. Now, this is f times g of negative 2. Now, let me just enlarge this just a little bit. Okay. So everybody pay close attention here now, please. So what we have to do is we have to understand a couple things. If you don't like this notation, that's fine. You could write that as f of negative 2 times g of negative 2. And that might make a little more sense to you. Because f of negative 2 is an actual value that we can get from the graph. And so is g of negative 2. So let's see here. Let's go to the graph. Which one is f? Okay, f is the dark blue one. Okay, good. And so at negative 2, this is x equals negative 2. So I want to find out what the value is of the blue graph at negative 2. And I wonder if that's supposed to be going through 3. Yeah, I think it is. That's supposed to be going through exactly 3. It looks like it's a little bit under, but if for some reason it's really strangely asymmetrical here in this diagram. Whatever. So we're going to say that's 3. I'm pretty sure that's supposed to be 3. So this is what you do. You just fill in a 3 there. You see that? F of negative 2, according to the graph, is 3. Now we don't need to know what the function is, right? We don't need to know that it's a parabola, x squared minus 1. We don't need to know that. All we need to know is that we can see the y value from the graph. And g of negative 2, so at the same negative 2, I'll put my red pen on, and we got to go down. Where does it touch the red graph? Well, at y equals negative 1. Does that make sense? And so what's the value for a? It's negative 3. Now we don't see negative 3 on the graph anywhere because we haven't graphed f times g of negative 2. We haven't, or f times g of x. We haven't graphed that line, so we don't see it on there. But we can get the information from the two graphs. And for those of you that are going to take AP calculus, this is very, very important. You need to know how to read graphs. Okay, very, very important. So you need to have a handle on this. Okay, and you guys will be great. Okay, so let's take a look at D then. Let's skip all the way over to D here. So D, f over g of 1. Okay, no problem. That's f of 1 divided by g of 1. Does that make sense? So f of 1 is what? Ooh, f of 1 is 0. I know already what this answer is. Unless g of 1 is also 0, then we have a problem. But if g of 1 is any real number at all, the answer is 0, right? So what's g of 1? Let's go up here. It is 2, right on. So 0 divided by 2 is 0. Awesome. Okay? So remember, 0 divided by 2 is 0. If 0 is on top, it's 0. If 0 is on the bottom, trouble. Okay? Trouble. It's undefined. All right. So let's just quickly do C here. F over g of 0. So f is negative 1. F of 0 is negative 1. And g of 0 is positive 1. So what's negative 1 divided by positive 1? It's negative 1. So don't get confused. Say, hey, we got a 0 here. How can the answer be negative 1? Well, remember, this 0 is the input value. What we're actually looking for is the f, the y value of each of those functions evaluated at 0. Okay? So the input value just tells you where on the x-axis that you need to go to look at the different graphs. Okay? It's just the vertical plane that you find the values for. Good? All right. You guys are awesome. Awesome, awesome, awesome. Okay. So, yeah, basically that's 10.2. Like I say, I spent a lot of time on that one example in previous years. I spent a lot of time on that one example. But because of our time crunch, because we're just combining the lesson here today, we're going to go right to 10.3. Because 10.3 is composite functions. So I will be giving you an assignment for 10.2. But right now we're just going to keep sailing right into 10.3. Okay? Because 10.2 is super easy, right? You guys good? You guys good with efficiency? and getting things done in short order?
Yeah.
You guys good with that? Right on. Okay, so 10.3. So I want you to write up, write this in your notebook. Okay, what we're talking about here, the title technically would be Composite Functions. Composite Functions. And I did mention this, I think, in 10.1, that we were coming up to something like this. And composite functions, if you think of the word composite, okay, or the root word of that, composed, right, it's kind of sort of what it's made up. It's what it's made up of inside. It's like what is inside of it, okay? Well, this substance here is composed of, wood and lead and metal and rubber and, plastic and all that sort of stuff. That's what it's composed of. That's what's inside of it, okay? So a composite function would be a function that's composed of other functions. Not in the addition, subtraction, multiplication, or division sense, but in the sense where one function is literally swallowed up by another function, or one function literally jumps inside of another function. It's kind of like jumping inside of a wormhole or a time machine or something. Okay, maybe not that exciting. A wormhole, I don't think would be exciting. Time machine? Yeah, give me a time machine. That'd be great. Okay. All right. So this is some notation here. F of g of x. So you see that g of x is actually inside of the f function. Okay, so this is different than what we've landed on before. So let's take a quick peek at this, okay? And actually what I'm going to do here is I'm going to make this 2x plus 1. I'm going to make this green as well. Actually, I don't really have green handy, so I'm going to make it gray. So g of x was, what was it again? 2x plus 1?
Yeah.
Okay, all right. So g has to go inside of x. So what is g of x? Well, this actually is g of x, right? That's the expression for g of x. So this whole thing has to go over and go inside of the f function. Now, where would it go? Well, it's got to go into the input place, right? Which is x. So that's there and it's there. So let's see. So f of, okay, g of x looks like this. F of 2x plus 1. It's not just x anymore. It's actually the other function. And that's going to equal, right? You love this color coding, don't you? 2x plus 1 squared. Okay? So you see elements of both functions, right? You see the g of x is right here. It's right here. And you see the f of x as well. The f of x is this sort of entire thing, right? That's like blah squared. See, f of x is blah squared. Just like this thing squared. And so here it is. It's this thing squared. So do you see elements of both functions? Composite functions as well. There's a ton of this in calculus. Okay? So yeah, if you can understand this lesson, right, this is a solid foundation for calculus. Okay, now can we do g of f of x? Ooh, can we do g of f of x? Sure we can. Why not? What's that going to look like? Well, let me just make some space here, because I don't want to erase what I've done so far. Oh, that didn't work. Let's try that again. Well, so g of f of x, okay. So let's say I'm going to use this all in red now. So g of, okay, so here's the parent function really is 2x plus 1. And the f of x now has to go inside the g of x. Right here, see? So we've now got what? 2 times, what is f of x? X squared plus 1. Ooh, So the g of x function is this 2 blah plus 1. The f of x function is the x squared. Everybody see that? All right. So it's kind of like the output of one function becomes the input of another function. The y values, or the expression for the y values, becomes the x values of another function, composed. Okay. All right, let's put some boots to the ground here and let's get this figured out. So here's our notation, right? You guys can understand this. It's the outside function would be f function and the inside function is g. Now what happens if I don't have an x here, if I have an actual number? Does that make things a little more complicated or not? Maybe one extra step, right? So what this means is we need to find out what g of 3 is. And that's no problem. Well, here's our g of x function. So this is going to be 3 plus 6. Or g of 3 equals 9. Right? So you always start on the inside. Start on the very inside and start working your way out. So now 9, guess what? Goes in here. You see, this is actually a value of 9. So that's now, it's f of 9. So let's now go over find f. Oh, here's our f function. Thank you much. And this is going to be 4 times, what's our input now? 9. So this is 36. So f of, I'll just rewrite this, f of g of 3 is 36. Okay, absorbing. Am I seeing the little circles going around and round in your heads right now, or processing? Okay. Any problems with that? You don't understand? Thank you for saying so. Okay, so let's. So what we need to do here is start on the inside. Let's do b. Okay, we're going to keep going. So let's do b, and we'll take another look at it. So this is g of h of negative 2, correct? So what we need to do is we need to start on the very inside. Well, the very inside, you might say, is this negative 2. Okay, well, do I have to do anything with a negative 2? No, that's kind of like a given. So let's start moving outside now to the next level. So here's the next level. So can I figure out what h of negative 2 is? Yeah, sure. Here's h of x. So that's actually, so h of negative 2 is actually negative 2 squared. See that? Okay? So I can figure out what h of negative 2 is. H of negative 2 is positive 4. Am I done? Not quite done yet. Now I need to find out what g of h of negative 2 is. Well, g of h of negative 2 is actually g of, what's h of negative 2? It's actually 4 here. You see that? So we start in the middle and then start to move outside. And we could have many, many layers. We just kind of keep evaluating and moving out. So g of 4, here's the g function. That actually equals 4 plus 6 from here. Okay? So g of 4 is 10. Therefore, from our original question, g of h of negative 2 equals 10. Okay? So here's the funny thing. A function could go inside itself, too. We put a function inside of itself. That's what C is. I know, that just seems wrong, doesn't it? h of 2. Okay? Let's focus on the h of 2 first. Well, h of 2, where's h function? Right here. Equals 2 squared. You see that? So h of 2 equals 4. So now I know that this is 4. Now I evaluate h of 4. Okay? And h of 4 is 4 squared. So h of 4 is 16. Now, does everyone see that? That's with those functions. Now, what I'd like to show you, just one more thing, is this, h of x. How do I show that as an expression? Well, you put h of x inside h of x. So this becomes, okay, here's the outside h of x, and guess what's going to go inside? That's fun. Isn't that fun? Totally fun. So that's x to the what? Fourth. Okay. So watch this. H of x. I don't know if I'm freaking you out here or not, or if this is totally making sense. But look at this. H of 2 is actually 2 to the fourth, which is bum-ba-da. You see? All works out. This is what we did. We did it first with an actual number and evaluated a number answer at each step. But you could also treat the function as, in terms of x, and you could do the same things with the function in terms of x and end up with an expression. Okay? I know this is super exciting. I'm glad you guys are enjoying this as much as I am. Oh, tongue in cheek there. Okay, let's see. How are we doing for time here? Okay, let me just see. Look at this monster lesson. See this? Oh, that's the same question. Oh, just a little bit different notation. Okay, look at this. Monster. Okay, so let me just talk about the domain here. Okay, last thing for this combined lesson, because really it starts to repeat itself here. Okay, and yeah, let's just do this domain part, because this is the last major thing in this lesson. Okay, so remember the domain, right? So with composite functions, okay, the domain, what is the statement for the domain? Let's see if we can find it. Do you think it would be the same as with the other functions? Any ideas? So does it make sense that the domain has to be the overlap, okay, or what is common to both? So look in your textbook. Actually, I'll get it up here for you. Okay, this would be on this page here, I think. So the key idea is, check this out at the bottom here. The domain of f of g of x is the set of all values of x in the domain of g for which g of x is in the domain of f. Whew. That's crazy, isn't it? Restrictions on the inner function as well as the composite function must be considered. That's what that means. So we need to take a look at g of x. Are there any restrictions there? Note those restrictions. Are there any restrictions on the larger function f of x? Note those ones as well. So basically it's kind of the same as overlapping, really. Okay, so let's take a look at this. If we had this as an example, f of g of x, okay, so f of x would be the root of something, and the g of x part would be that something. So I have that labeled over here, which actually you might not be able to see very well. Okay, so here is f of x, that's the outside function, and here's g of x right here, which is the, g of x, which is the inside function. See that? All right, so let's start off with the inside function first. Are there any restrictions? No restrictions. We're not taking the square root of a negative number. We're not dividing by 0. No restrictions. But what about f of x? There are restrictions for f of x. So guess what? This inside value here cannot be less than 0. It has to be greater than or equal to 0. Does that make sense? So that means now, because we're putting g of x inside there, okay, then now this x is actually g of x. So it's not necessarily an overlap, but it's kind of the same. You take both into consideration. But if you have a restriction on the outside function, that restriction has to be applied to the inside function. So let's say it that way. I'll say that one more time. If you have a restriction on the outside larger function, that restriction has to be applied to the inner function. And then those x values are the ones that you're focusing on. So hopefully this is making some sense here. Because the input for this square root of x function has to be greater than or equal to 0, that means that because this function is the input, that this function has to be greater than or equal to 0. Okay? So if we solve for x here and get x all by itself, we know that x has to be greater than or equal to 3 over 2 to make sure that this square root is positive underneath there, or 0. So this is now our domain. Okay? Any questions?